Hello and welcome to this video. Today I'm going to talk about diagonalization, so matrices and endomorphism, addend values, eigenvectors, and spectra. Okay, so let's go quick. Definition. An eigenvalue lambda of a matrix A is so that lambda ID minus A is not invertible. Okay, so to study that, we'll actually calculate the determinant of this thing. A spectrum is the set that contains all of the different value of a matrix in a space, for example reals. An eigenvector associated of an eigenvalue lambda is ker lambda id minus a. The characteristic polynomial key, so Greek letter key. Sometimes I say polynome, but it's polynomial, but because I'm stupid, because I can't speak English. It's the polynomial variable x, so that key a of x is equal to determinant x id minus a. So there is an old notation with a here and x minus id. So it can happen too, and I still fall on that trap. But whatever. So the only difference is a sign, but it doesn't matter to study that. So for French English disambiguation, in French SP is the spectrum, so usually real, of an endomorphism A, but in English span of A or SP of A is the linear span of a set of vector A. But in French we call that vect. So I'm going to use the French convention. What is diagonalization? If A is a matrix, then a diagonalization is the operation to get D, a diagonal matrix, and P, a change of base matrix, both having the same size as A, so that A is equals to P minus 1 dP, or A equals to P dP minus 1. Both conventions exist. Few theorems exist to say if a matrix is diagonalizable or not, but we'll study only in the case that is diagonalizable, not trigonalizable. So we'll just study the case that it is, but you have to know that there exist lots of things that exist. By a theorem, D is equal to the diagonal matrix. That is actually, this formula is kind of complicated, but basically you have all of the eigenvalues, but and if its multiplicity is non one, you'll have multiple times. So if its multiplicity is 2, you'll have twice that eigenvalue. So P and P minus 1 is equal to all of the eigenvectors that are actually set together. So we'll do an example. Why is it that big? I don't know. So I call a matrix like that. So I have key A of x is equal to the definition. So I calculate that and we get this matrix. We just did like the definition. So we have this. We can use the formula of Sarus. It's a very important rule that says that the determinant of a 3 by 3 matrix is actually this times this times this plus this times this times this plus this times this times this minus this times this times this minus this times this times this minus this times this times this. By Sarus, we do that and we get we get that. So I just simplifying and we get we get this, so x minus 2 and times x minus 4 squared. So this is the first method. The second method is actually developing. So we have this matrix that is actually the same as this one, and we'll develop from the first line. So we have x minus 3 times the determinant of this one here, so we have this one, minus 0 times the determinant of this matrix here, but since it's plus 0, it doesn't matter, plus 1 times the determinant of this matrix here. So, so we are on that step. We have x minus 3 that is actually equal to the determinant of this. So to determine determinant of a 2 by 2 matrix, you do this times this minus this times this. So we get x minus 4 times x minus 3 minus 0, but times minus 2, but 0 minus 2 doesn't matter. And that's it. So we get this part here. And for this, we do minus 2 times 0, so that equals 0. Minus 1 minus 4, so we get minus x minus 4. We simplify that, and we get x minus 2 times x minus 4 squared. Now we'll find the spectrum. So here we get two eigenvalues, but the matrix is of dimension 3, and since there is squared, we know that the eigenvalue 4 will have an order of the multiplicity of 2. So the spectrum is equal to 2, 4, to the set of 2, 4. The multiplicity of 2 is equal to 1, and the multiplicity of 4 is 2. And since the dimension of the matrix is 3, so it's a 3 by 3 matrix, it works. So we have all the eigenvalues. Step 3, find the eigenvectors. So to do that, we'll as we've seen in the definition, here we'll be worried about this. So A minus the eigenvalue times the identity. So we'll start with the eigenvalue 2. So 2id minus A is equal to this matrix. And actually, we'll do this, but transform it into a system. So minus 1 becomes a minus x, 0 times becomes 0 y, and 1 becomes z. So for the second line, minus 2 becomes minus 2x, minus 2 becomes minus 2y, and minus 2 becomes minus 2z, so you get the idea. And we equal that to 0, that's the definition of care, the operator of care. And we get this by simplifying. Here I just did plus x. Here I just replaced, and we get this. So we need to find the vector that that is the linear span, so the vect in French. So what we'll say is we'll just set x to be 1. So I just set to x equal 1, but z equal 1. So z equal 1 because z equal x. So we have this one and this one, and to find the y value, we have y equal minus 2z, so minus 2, and then we have our stuff. So now we calculate 4id minus a. So we get hold on a sec. I have something to check. So yeah. So I was thinking something about the eigenvectors because they look slightly weird. We have this differential system. We'll do the same thing again. So we'll get this system. We solve it and we get that x is equal to minus z everywhere. So this means that you can the first vector that will generate the eigenvector will be x equal minus z. So we'll have if we take x is equal to 1, then z is equal to minus 1, and then we'll put a 0 in the y value. And since the multiplicity of 4 is 2, it means that we'll have a 1 here because the eigenvectors of the eigenvalue 4 will generate the space for all values of y. So we get this, and since we know that we have our diagonal matrix and this matrix of change of base, we are pretty much done. So that's it. To go deeper, we can like do stochastic matrices and recurrences, but it's slightly more complicated, and I'll cover it in another video. So I hope you liked it, and if you have any questions, feel free to ask them. I'll be glad to answer them. And bye.